Welcome back. And the next talk is by Joel Hirschi from National Oceanography Center, Southampton, and Joel will talk about global high-resolution modeling of ocean and climate.
Okay, well, thank you very much. A pleasure to be here. Very interesting. And so next 20 or 25 minutes or so, I'd like to say a few words about well, what we do, what sort of models we use, where we got to, what the challenges are, and also with some views as to where machine learning could potentially help. I mean, I'm not an expert in neither machine learning nor things like surface waves or rogue waves, but I've got my broad field is really in numerical modeling of the ocean. And rather than say too much about it, I thought you can have a look at the movie that is playing here, which is from one of our models, 1/12 of a degree global model, NEMO model. It's the NEMO model, which is the European model that is used in many places, that is developed jointly between the UK, France, Italy, and there's some Canadian partners as well. So this essentially illustrates broadly what the state of the art is in terms of a ocean model component that one can run on a climate timescale. By climate timescales, I mean multi-decadal up to perhaps a century or so. And what it shows are surface velocities. You probably have guessed that. So white colors showing where currents are strong, blue colors where currents are weaker. Recognize some major features like the Gulf Stream here, the Kuroshio current that some of you probably will know. And one feature that is quite always that is striking is how complex that circulation is, that multitude of little swirls and eddies that are ubiquitous across the ocean that are called mesoscale eddies. And so this is basically what we have at the moment. So our most advanced models, they do tend to represent these eddies. They're not perfectly resolved, but they can simulate them to some degree. And when you compare that with satellite observations, that looks quite comparable. And this is from a global model. We also do, if we zoom in a bit more regionally, this is an example from the North Atlantic. You get even smaller features appearing, even if you have these big swirls that you can recognize here. If you zoom into those, you can see that they themselves have some little ripples along their fringes, which are called submesoscale features. And this is where the field now is moving towards, where the absolute cutting edge now is moving towards having global models that can represent these little sub-features that you have on top of the mesoscale. And here, next, perhaps to say a few words about the interesting processes that we have in there, it's important to highlight that this is not just the ocean. And so these features, all these swirling motion, there's something quite universal about them. And you can find them everywhere. So the ocean, obviously, that's one that is closest to my heart. That's what I do. But you will find them virtually everywhere in our environment, ranging here from the background. This is just an example, a puff of smoke. So you see very similar features. But you can have that on a whole range of length scales, ranging from here an example that I took when I did the washing up, just some eddies in a washing up sink. Doesn't look too different from what you have here. Underlying forces, force balances, not the same, but features looking very similar. And then moving to slightly longer scale weather systems on Earth, again, you can recognize the swirling features presented by the clouds. Same thing if you go to other planets, Jupiter, you can have even cloud bands that you should have all seen that also have these swirling features that are indicative of eddies happening with scales that can be up to roughly 10,000 kilometers. And going to very, very long length scale of light years, distribution of structures of interstellar dust, which again can have very similar structures, and depending how you look at them, if you remove the scale, it would be hard to tell which is which. And so this is all shows that this is something, so there is something universal about what we're trying to understand there when we have these motions in the ocean, by trying to understand how these eddies work, that has relevance for a much broader range of fields, and there are parallels that are very interesting. And so I thought that the audience here, some of you have background in mathematics or chaos, and so that's perhaps interesting to highlight that how many overlaps there actually are, even though the actual balances of forces governing how it exactly works in these different environments are not necessarily the same. The results and how it looks visually may be very similar. Now, just briefly to say how what we do is working. So essentially, you will be familiar with this. Essentially trying to solve a set of equations, in our case the Navier-Stokes equations, that you will be probably, quite a few of you will be familiar with. You can't solve them with pen and paper, at least not analytically, so they have to be solved numerically. So we have to convert that into some computer code that has to be then run on a computer. For the example that I've shown before, it has to be a supercomputer. Shown here is Archer 2, which is the main supercomputing facility in the UK, based in Edinburgh. And this is how we actually get these results. Now, here it is perhaps useful, since I mentioned computing, to remember ourselves where we came from in terms of computing power. And this graph here illustrates the computing power, the peak performance of the most powerful machine that was available since the 1960s. And if you just look at the most powerful machine, there has been a 12 order of magnitude increase in the peak performance of these machines. So it's an absolutely staggering increase of computer power. Here in red, the red triangle illustrates where Archer 2 is. This is the machine that has come online last year. It is nowhere near the most powerful one, but it's a pretty good machine. It allows us to do lots of things. This one here, the top one, I think that is probably Oak Ridge Summit in the US, I think the first official machine that is officially an exascale machine, exascale being 10 to the power of 18 floating point operations per second. Now, so this is essentially what we have at our disposal now, but it's quite interesting and sometimes humbling also to go back in time a bit and see how long ago the first simulations that were, the first simulations that actually were able to represent some of the sub-mesoscale features I showed in my initial animation. So the first simulation that showed features like that was actually done in 1977. So that is quite impressive, 45 years ago. So that is always good to keep in mind. So we really, what we're doing now really builds on a lot of work that was done decades ago, and we still benefit on that, and the legacy of that still lives on into the codes that we are using today. So late 1980s is when we had the first example I've come across of a global model that where we could simulated some eddying features in the ocean on a global scale, not just regionally. And then moving on closer to present, 1990s, there was a flurry of activities where the eddy permitting models were developed, but they were quite simple, very few vertical layers, not much resolution within the body of the ocean, or they were run only for a very, very short period of time. So you couldn't do anything that was perhaps from a climatic point of view that useful quite yet. There was more kind of a proof of concept that we can do that, and then compare it with early satellite observations to convince us that what the models were doing was quite similar to what we saw, what we could see in the real world. And now, moving from the, let's say, early 2000s onwards to now, So this is when we get the type of, now that the developments that led to the type of models that we have now. So we can have these typical sharp fronts in the ocean that are associated with the Gulf Stream or the Kuroshio that are very important for AC interactions and for the genesis of some weather systems as well. And the better exchanges between the shelves and the open ocean, which is one area that has lots of activity. Now, just to show you another example of where we stand now in terms of coupled modeling. So before, my first movie was just showing the ocean on its own. Now, if you want to do climate, we need to couple it, obviously, to the atmosphere. So we want both systems, the ocean and the atmosphere, talking together. So this is a kind of the projector is not quite keeping up with this. It looks very blocky. So apologies for that. So it looks much smoother on my screen, but that's okay. That's a gig, so it should be enough to give you the impression. So what you see here again, blue color, the same as before. Red are bands of rainfall in the atmosphere. I should have said the ocean has a resolution of 1/12 of a degree. That's around 8 kilometers resolution. The equator, around 4 kilometers in that region here in the North Atlantic, for example. The atmosphere has a resolution of 25 kilometers. So it produces storms. It produces its storms. It even produces tropical cyclones. But obviously these cyclones, tropical cyclones, are not properly resolved. They are tropical cyclone-like features, but they don't have all the dynamics that a real tropical cyclone has. So I would call that tropical cyclone permitting in terms of models. So essentially, this is the type of model that we have now that is at the, I would say, at the cutting edge of climate models that are run on timescales for about 100 years. So that particular model here, collaboration between the National Oceanography Centre and the UK Met Office, was run for 100 years. So that's broadly what we can do. There are similar things have been done in the US, and other colleagues in Europe and Japan have produced similar simulations. Now, so this was just to illustrate where we're standing now. So that's where we are. And just to make that clear, that particular model here, the resolution is much, much higher than any of the CMIP6 models. For example, the IPCC report that you probably have heard of is based on models that have a much lower resolution than that. You wouldn't have all these eddies and these sharp fronts typically. Now, I thought it might be interesting to say a few words about waves, because I saw that the program is about waves, and as I can see, there's lots of wave-related expertise in there. So this result is the result of solving the Navier-Stokes equations, and that contains many waves. Not rogue wave, we wouldn't have that. However, just what I want to say here, okay, some applications that we had for that models, trying to understand the winter storms, things like hurricane activities, but also ocean influences on things like cold spells or hot summers like we had this year over Europe. So there are reasons to believe that the ocean has some mounting evidence that the ocean is not just a passive player in the whole thing, but it is actually actively can actually drive the atmosphere in some instances. Now, going to what I wanted to say before about the waves. So there's a whole variety of waves that these models do represent, things like Rossby waves, Kelvin waves, equatorially trapped wave, boundary waves. And here an example that perhaps is not that well known, but I think looks quite nice. These are near inertial gravity waves that are triggered in the ocean by passing storms or weather systems at high latitudes in the northern and in the southern hemisphere converging towards the equator. So these features exist in the real world. So we know that the near inertial gravity waves are ubiquitous in the real world. So all these waves are key for how a circulation spins up and develops in the model. However, we still miss many processes in there. So things like braking for waves. Essentially, what we often have, the Rossby wave I mentioned before, are often internal waves that occur at the interface between water of different densities. They move across the ocean, set density gradients across the ocean, set up the currents, and when they change, and they can modify currents on timescales of years to decades and multi-decadal. So they are quite important to understand how the circulation develops and how it may change as, for example, our climate warms. Things that are not particularly well represented or not at all represented in none of the climate models at this stage is how internal waves, they can break, they can cause mixing. This is something where we have to rely on parameterizations. This is not something that a model like that does represent. So this mixing is done in a rather crude way. We have to rely on parameterizations. We cannot resolve that yet. So it's just too fine scale for us to resolve. Now, moving to surface waves, which typically we don't have in these models either. So there are no surface waves in that sort of waves, so that we could not have rogue waves here. However, these waves might be important. They might be very important for things like how they interact with sea ice, for example. My question of my colleague from NOC, Evgeny Aksenov, maybe some of you remember, he asked a question about that after Peter's talk. Well, the idea there is that as the climate warms, sea ice is thinning, waves can encroach more under the sea ice, may actually break it up more easily, and even hasten the decrease of sea ice. This is something that is completely missing of all the climate models at the moment. So something to keep in mind, one process. So there are many wave-related processes, just giving some examples here, that our models are failing to capture, and the jury is still out as to how important they are. That is not 100% clear yet. However, one would perhaps should not be dismiss them before actually having tested how much of a difference it makes. And there are people who are working on that. So I was pleased to see Hendrik's talk before, coupling WaveWatch 3 to, I think, models that are actually not too dissimilar from what I'm showing here. So you can actually couple these systems together and then have that information and then feed it into a climate model that then hopefully would lead to a more accurate forecast or also of impacts, what you can expect, for example, in coastal regions for future weather extremes. Now, moving to some of the challenges that we face. So one of the main ones, I think at least, some of you may disagree, but certainly from what I'm encountering myself is the challenge to actually analyze the vast amount of data that these models are producing. It's not just the computing power that has increased by order of magnitudes, so has our ability to produce data. And in my view, it far outstrips our ability to actually analyze it. And that is something that is certainly holding back our field. So we're not very good at churning out huge amount of data. Models like the ones I've shown before can easily produce up to 1 petabyte of data. If you have 100 years of data, your output is perhaps, don't know, daily. Well, you end up with petabytes of data if you have that. So that is not something you can just you cannot load that into MATLAB and play around with it. It just doesn't work. So this is certainly one of the areas where I would think things like machine learning are heavily underexploited, and where there are lots of things that we cannot do, but which machine learning could be extremely helpful. And it is done to some extent, but it is not very common. Certainly at my research center, some people use it. I've used it here and there, dabbled in it a little bit, but I haven't seen much of a concerted effort to do that. So, but it's certainly an area where I think there could be there is some potential. Now, another challenge is, I mentioned the staggering increase in computing power and our ability to produce data. However, even with what we can do now, we're actually far away from being able to exploit these latest HPC facilities. So all the codes, I mentioned that before, some of the legacies go actually back pretty far. And so they were not originally written to be run on these machines. What made these machines so fast is not only a speed up in the processor speed, but in how many processors such a machine contains. So the biggest machines can contain in the order of millions of cores. And this is something that at the moment we cannot easily exploit when we run a model. That is something that requires actually a massive amount of work, and there are efforts ongoing in Europe and elsewhere, also a bit here in the UK, trying to port that model to exploit GPU, graphical processing units that are very well designed for parallel tasks, and to exploit that to speed up our models. So this is something, but at the moment that is still quite in the early days. So it leaves us at the moment, we've got machines that are fantastic, but we can't fully exploit them, and that is frustrating. And the effort actually going into making these models up to scratch for exploiting these latest architectures, there's normally not sufficient to really do that. So it's happening a bit on the fringes. That certainly my feeling is more could happen more broadly in the community and elsewhere, perhaps together with industry, to get to optimize that process, because it's a lot of work and it's not easy to do. It's hard work and sometimes scientifically not very rewarding, but if we don't do it, we may miss out on things that we can do, and we can exploit what we have. Now, moving towards the last part of my talk, a few thoughts about machine learning. Something that has come up quite a lot in our community, and perhaps in news as well, you may have heard about moving towards digital twins of the Earth, having a digital twin of the Earth. For example, there is a major project going on in Europe at the moment called Destine that has the goal in the next 10 or so years to produce a digital twin of the Earth that would consist of a model like that, but even higher resolution. So they're aiming for a resolution of a roughly kilometer scale. So it's quite a bit of a beast. So it's early stages. I know that ECMWF is involved. So Peter, you may have heard about that. I know that I think the first steps have been done with the EFS model, from what I understand, which is the international forecasting system run by ECMWF. So one step is going to be to create a system that has a kilometer scale in the ocean and in the atmosphere, and to be able to run that. And the aim would be to be able to run that for at least, let's say, a couple of decades, or at least also be able to do forecasts. So like that, for example, to be able to run it, let's say, up to 2050. And that's broadly what probably just about would be possible nowadays if you really exploit the very, very best that we have. But we're not there yet, but that's where things are going to be moving in the next couple of years. But even if we manage to do that, we can only do at max perhaps a few simulations, not many. We can't afford to do many of those. It's going to be very, very expensive. And actually also environmentally emits lots of CO2. One thing that has increasingly to be taken into account, running these big computers uses lots of energy, so not to be neglected. So how can we then, the idea is to machine learning could then increase what we can get out of these efforts. And the idea there would be, and Hendrik touched on that, and so I think it's probably the same thing that Hendrik was touching on too. I looked around a bit what was out there and came across a nice little effort that is sponsored by NVIDIA, that is to create a digital twin of the Earth called Earth-2. The idea is for them to use, they're going to use GPUs to do that, obviously. I mean, those of you who are into gaming will know that NVIDIA is one of the leaders in a graphics card. And the idea there is to use machine learning to create an emulator of of the more complex system. That can be either the model, it can be based on observations, so it can be reanalysis data, that can be trained. You can try a neural network, use machine learning to create an emulator that can capture the main feature of the system. It doesn't contain the physics, so it's not solving the equations anymore, but it feels the physics through the data it has been fed to train it. So, and the advantage of that is that it can be run very, very fast. The idea there would not be to run it then for decades. That wouldn't be very smart, because it's something that if you run, because you may then run, you may end up very far away from the training period and may do that your neural network may not be good for that. However, it may be good for short periods of times. And what you could do with that is to run it many, many times. So you could create, even though it's based on information from a very complex system that is hugely expensive to run, there is the potential of doing perhaps thousands of ensemble members that are better and suited to sample the tails of the distribution of events, of extreme events, being storms, heat waves, floods, or marine heat waves in the ocean, and see. And that could be done, for example, for different times. Let's say one focused around the 2030s, one focused around the 2040s, and see how something is likely to change, the distribution of extreme, what sort of extremes are we likely to expect in 10, 20, 30, 40 years from now, and then perhaps provide some valuable information on how to prepare for it and how to either coastal defenses or how to build houses, you name it, lots of things or healthcare, what things to look out for and what the main extremes could be, because that's where the damage tends to happen when we have an event that punches through the roof of what you've experienced before. And it's basically on this that I'd like to conclude. And essentially just this is a brief summary of what I said. The high resolution models is key to have a good, faithful to reproduce, simulate climate realistically. But there are lots of things that are still missing. On the wave side in particular, there's still a lot of work that needs to be done. Certainly on the ocean side, there are many things missing. And so definitely more should be done, could and should be done. And we're now at the beginning of the exascale era. And so in the very near future, we're going to have the first kilometer scale simulations available. However, to really make the most out of these things, quite a few challenges need to be overcome, and how to use in terms of what I said before. And machine learning may be a very good tool to help us with that, because it can help on various fronts, can help us with speeding up the analysis of data, pointing us where to look more detailed to understand the physics. Machine learning doesn't understand the physics, but it may actually point us and help us, guide us a bit where to look and think about it more carefully. It may help us to improve parameterizations of model and help us to include things that we cannot resolve by improving parameterizations, or, as I said before, use of emulators that can actually used in many ways. So, and that's where I would like to conclude. I'd like to thank you for your attention.
Thank you very much. Lots of questions.
I just want to make a remark. The operational forecasting system of the European Centre consists of a coupled system, atmosphere,
yep.
ocean circulation, mm-hmm. and ocean waves.
You have already needs an EMO model, actually. Yeah.
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 We of course use, for practical reasons, a coastal resolution model for the ocean, but we have serious problems still with the separation of the Gulf Stream. So does that improve in your system?
Yes, we have.
Are you sure about it? Because
yes.
We tried it. We don't see anything happening there, really.
Let me go. I should go back to the very first slide. Okay. This one here.
Mm-hmm. Where's Cape Hatteras?
This is Cape Hatteras here.
Okay.
It's a pretty good separation. It's pretty good. I know that there are, which resolution are you talking about here?
A quarter.
Yeah, the quarter doesn't work. The 1/4 consistently overshoots here.
Yeah, so
Yeah,
it's
yeah,
too
yeah.
late. And you can see
Yeah,
that
yeah.
immediately in the forecast.
And it's not a guarantee that it works at that is 1/12 of a degree. So there's a big difference between 1/12 and 1/4 in the ability to simulate that. And however, if you look out in what our colleagues are doing worldwide, I've even seen models that have a 1/30th of a degree resolution, and the Gulf Stream still overshoots. So it's exactly what keeps it in place there is not understood yet.
But you must have done something because you have it right.
Well, no, it just no. It was it may be a fluke, but no, we didn't fiddle around to make it. So we played around a little bit with lateral boundary conditions. You can have a free slip, no slip, partial slip. That seems to have a bit of an effect, but yeah.
Okay.
I think.
What do I do?
Yeah, that's living in that area. We definitely like that better, to get that better. But from a climate perspective, I assume you agree with the fact that you have to go through something like a 12th of a degree to be able to get the north-south energy transport properly done, and especially if you do the longer forecast ranges, then the 1/4 of a degree just you have to parameterize the eddies locally to make them look good, but then your northward energy transport is not particularly good. And I don't think it's the final answer, but some of the interesting high-resolution stuff I've seen around Cape Hatteras, it seems to be a very subtle three-dimensional interplay between the Gulf Stream and the Labrador Current going underneath it, and how they exactly mix. So it is interesting to see how a very local problem just in that area can have such an impact on a big part of the North Atlantic to begin with.
Yes, and it's an important region. Yeah.
Great, yeah. Thanks for sharing. It's really great to see the coupled models and the sophistication as we move towards the kilometre scale sort of physics as well. And a question on the atmosphere-ocean coupling part as well. So, I mean, the depth discretization for like NEMO or this class model is like 50 to 100 levels. So there's an absence of momentum transfer vertically with that as you move towards high definition models. So I think there's a risk of losing wave activation modes with that. So can we use machine learning techniques to help fill in those gaps? As you go to a kilometre, do you need to go to 1 centimetre? No, levels. Otherwise, you're going to get all sorts of reflections.
I don't know how far we would need to go. However, it's certainly an area where machine learning could potentially, as I mentioned, could be used to improve parameterizations. So that could account for what you just said. So I think that is a promising area, and there are some people who have used that and are using it to do that. Yes. So my answer would be yes. It's something that is worth looking at.
Thank you. There are some online questions.
Yeah, just one quick question from online from Karima. So how can one test simulations on the scale of 100 years?
Well, we have that's a good point. We have reanalysis data, so we have observational data sets that go back 100 years. So for some regions, we can do that. Globally, we have reanalysis data sets. So reanalysis itself is a model. So essentially, it's feeding observations into a model and let the model fill the gaps. So that's what a reanalysis is. And so this is, at the moment, this is our best bet that we have to compare our global models to the real world of the last couple of decades. And obviously, if you want to go 100 years back, it's very patchy. But there are some data sets, like the Hat-Krat data set, they put together, so for some quantities, temperatures, at least, temperature anomalies, where you can actually do that quite well. Obviously, you can't do that then for other quantities, but there are some quantities that do go back 100 years. We can at least have an idea, feel as to whether you're completely off or doing something rather reasonable.
Okay, thank you very much. And then let's take our speaker again. So we have lunch break, so we resume it quoted. Oh, oh, there is a. Oh, sorry. Yeah, please. Oh yeah, I see. My bad, sorry.